Hello, and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. This is guided notes number 6 in the series on section 2.5a, polynomials in quadratic form. So far, we've talked a lot about how to handle certain kinds of polynomials. We've talked a lot about how to handle polynomials that are quadratic equations. The main idea of this chapter is to extend those kinds of techniques to other higher degreed polynomials, which may possibly have the same underlying form or pattern as those other earlier polynomial equations. The idea is that if we can simplify these polynomials in such a way that reveals a quadratic equation, or if we can make a variable substitution, which does, then we can apply the techniques from quadratic equations to solve those particular polynomials. Let me try to get a handle on what I mean with an example. Notice here we have a greatest common factor that can be pulled out of each equation. Even though it's a fifth degree polynomial, we can pull 3 n's out of this polynomial, as well as a 5 from both 5 and 180. If I divide 5n to the third from 5n to the fifth, I get n squared. And if I divide 5 from 180, I get 36. The idea is that now that we've factored out a greatest common factor, what remains is just a quadratic, and in fact a very nice quadratic, a difference of 2 squares. And we've seen that a difference of 2 squares can factor as follows. Now, taking advantage of the zero product property, we have that either 5n to the third is equal to 0, divide by 5, take the third root, or just use the zero product property again to see that this entails n is equal to 0 in this case. If n plus 6 is equal to 0, then perhaps n could be equal to minus 6. And if n minus 6 was equal to 0, then n would be equal to plus 6 in this case. So these three answers, 0, minus 6, and positive 6, are going to be the three solutions to this original fifth degree equation. Now, the fundamental theorem of algebra tells us that there should be 5 roots, but here we see that the root at 0 had multiplicity 3. And we recall that the fundamental theorem of algebra tells us how many roots there are when we count with multiplicity. So this would be 1 root, 2 roots, and 1 root repeated 3 times, making a total of 5 roots. Here we have a cubic equation, which we're going to be able to factor by grouping. But in fact, we might have to do a little bit of rearranging in order to do that. They've given us a hint about what that rearrangement might look like with the way that the 6 and the 2 have been arranged here. Still, in any case, I would begin this problem by setting it equal to 0. I prefer to keep my leading terms positive, so I would keep this on this side. I would bring over the minus 6k squared from the other side. I would bring over a minus 2k from this side, and I would leave my plus 6 right where it is. This is now set equal to 0, and so I can proceed to factor by grouping. Recall that grouping looks like cutting this thing in half and factoring the greatest common factor out of each part. Here I could pull a k squared, and in fact a 2k squared from each part, and what remains would be k minus 3. Similarly, I could pull a 2 out of each of these, but a minus 2 is especially helpful, because pulling out a minus 2 will change the sign of this second term and make it a minus 3 as well. And the main idea here is that having factored out the greatest common factor from each half, we have a repeated term. We have this k minus 3 that's on both sides of this difference. And what that's going to let us do is factor out a k minus 3. What remains will be a 2k squared minus 2. And let's even take advantage of this time to factor out that 2 out front. If I do that, this will leave me with k squared minus 1. And k squared minus 1 is again a difference of squares. So here we have another reduction that could occur. I can continue to simplify this by factoring the difference of squares. Now, what solutions does this equation have? Well, we're looking at the zeros. We have a product equal to 0, so it will either be where the first term is 0, the second term is 0, or the third term is 0. So we have solutions of 3, minus 1, and positive 1, respectively. I want you to notice that although it does change the polynomial, this 2 had no bearing on the zeros. Now, not every cubic polynomial factors by grouping, but factoring by grouping should be your first approach to try to tackle any cubic polynomial. That's, of course, one with a cube as its highest power. We begin by setting things equal to 0. We slice the polynomial in half and factor the greatest common factor from each half. On the left, that's x squared, which gives me x minus 6. And we're looking to produce another x minus 6 on the other side. That entails factoring out a 2, and in fact, a negative 2 will produce the x minus 6 that we require. Once we have this repetition of terms, we could factor out that single term, x minus 6, and what remains will be x squared minus 2. Now, this is not a difference of two squares, but that doesn't mean that it doesn't have its own roots. They're simply not rational. I wouldn't continue to factor this. What I would do instead is perhaps use the square root property. The first solution we could get, though, is a 6, and other solutions will come from setting x squared minus 2 equal to 0. If we bring this 2 to the other side and take plus and minus the square root, we have our two remaining roots. Our total roots for this problem are 6, square root of 2, and minus the square root of 2. Let's continue to apply this methodology. We begin by clustering things together on one side, changing the signs as necessary. We cut the equation in half, and we factor the greatest common factor from each half. On this side, that'll be an x squared, and on this side, we'll need to take out a 4, in fact a minus 4, from each term. That produces the 7x that we need, and also the minus 5. If you were to attempt this method and you were unable to get matching, you would have to abandon that method because that's a requirement for doing factoring by grouping. It's now that I have this repetition of 7x minus 5 as a term that I can pull that out front and write this as a single x squared minus 4 as its companion factor. X squared minus 4 is the difference of squares, and so it factors as such. 7x minus 5 equal to 0, from the 0 product property here, would tell me that x was equal to positive 5/7. And from these two solutions, we have x is equal to minus 2 and x is equal to 2, respectively. That gives us our three solutions, and we can have at most three solutions for a cubic. Here again, we cut things in half. We factor out an x squared. We get 5x minus 7 remaining, and we have 5x minus 7 itself as a second term. So I put some organizational parentheses in here to get your eye trained. The idea is that we're still going to divide 5x minus 7 from each term. But when I divide 5x minus 7 from the 5x minus 7, I require a 1 here to hold place. You could think about that as being necessary in terms of foiling this whole term back in to get the line above. And this, of course, gives us some complex roots to worry about. If I have 5x minus 7 equal to 0, this is going to give me x equals 7/5. But if I have x squared plus 1 equal to 0, taking the 1 over, I wind up with x being equal to plus and minus the square root of minus 1. That is to say, plus and minus I. And so we wind up with these three solutions, plus minus I and 7/5. First of all, let's notice that we could probably proceed by making this leading coefficient positive, or we could subtract over the 432v squared. It really doesn't matter. What I'm going to do now is divide out negative 2v squared from each term. And what I would wind up with is v to the third plus 216. Now, the question is 216 a cube? Because if so, this is the sum of cubes. Now, we could test that by taking the cube root, which is, of course, the 1/3 power, and we'd find 6. That is to say, 6 to the power of 3 is indeed 216. And a nice formula to have on deck for these kinds of situations is one more way that we can deal with cubic powers. If I know that we have the sum of cubes, it factors as follows: a plus b times a squared minus ab plus b squared. Now, just like the difference of squares formula, one can check this by foiling. If I were to foil an a against each term, what I would have is a cubed, and then other terms like minus a squared b. But when I put a b inside, I'll get a squared b, a positive that cancels that negative, or minus ab squared, where before I had positive ab squared. And the only remaining term will be plus b cubed. And so we see cancellation of all terms except for a cubed and b cubed. Similarly, there is a difference of cubes formula which looks very similar. The sign gets kept between the difference of cubes and this first linear term. And then we still have a squared, ab, and b squared here, but now we need pluses all around. You can check for yourself that these are true, and what you will find is that this quadratic equation is prime. It does not factor, and so to get the remaining roots, we would need the quadratic equation. Let's push this all the way home. So we have minus 2v squared, then the sum of cubes with v cubed and 6 cubed, so this is v plus 6 times v squared minus 6v plus 36, all set equal to 0. Now these two are of course v equals 0 and v equals minus 6 for the roots. But this one is going to require the quadratic equation. So we do negative b, which is positive 6, plus and minus the square root of b squared, which is 36, minus 4 times a times c, which is 36, over 2a. Now, I can't help but notice we're taking away 4 36s from 1 36, and that's going to give us minus 3 36s. I think that's nice because this is going to allow us to take out a 6, and the negative sign will come out as an I. So we wind up with, and dividing the 2 into both terms, we have 3 plus and minus 3 radical 3i. So here are our roots. We have a 0 with multiplicity 2. We have a minus 6 with multiplicity 1. And we have these two multiplicity 1 complex roots. That gives us a total of 5 counted with multiplicity. So what appeared to look like our first problem actually was a little different, because we didn't wind up with a difference of squares after factoring, but in fact a sum of cubes, which required these slightly trickier formulas. I think these are easy enough and worth memorizing. A nice way to write them both as one formula is a cubed plus or minus b cubed is equal to a plus or minus b, then a squared minus or plus, which indicates an opposite sign compared to our choice here, ab, and then plus, always plus, b squared. These next examples are going to involve variable substitution. The main idea is that although this is a fourth degree polynomial, it's not a general fourth degree polynomial. Notice there are no cubes, there are no linear terms. There's simply nothing for a variable, so a variable to the 0th power, a constant. There's something here, a t squared, and here there's something squared, that is to say t squared squared. The pattern that you are going to be looking for is a constant times something squared plus a constant times something plus some constant. If we observe this, then what we really have is sort of quadratic equation-like. We would say this has a quadratic form to it. And what we would like to do is simply identify that something and make a little substitution. I can see the middle term here is t squared. So to simplify our world, let's call that u. If that's true, then u squared is t squared squared, which is t to the 4th. And what we then have is u squared minus 26u plus 25. Now this can be factored. This can be factored u minus to match this plus, factors of 25 with the sum of 26 or 25 and 1. And this is still all equal to 0. Now the notion here is of course that we're not quite done. We need to reverse our substitution because our question was originally posed in terms of t's. So this says then that t squared minus 25 times t squared minus 1 is equal to 0. Notice then that we have a difference of squares, and this is t plus 5 times t minus 5, and t plus 1 times t minus 1. And this gives us our roots of t equals plus and minus 5 and plus and minus 1. 4 roots for this fourth degree polynomial. For the next one, we're going to want to take advantage of the same trick. We're going to want to see this middle term as being something that we would like to substitute. If I take x squared and call that u, then u squared is x to the 4th. And that gives us this quadratic polynomial, which we could actually factor. Now, you might think that 51 is prime, but in fact, 17 times 3 is equal to 51. And so we could factor this as u plus 17, u plus 3. Now, this, of course, doesn't give us exactly squares, neither does it really give us real numbers, because when I reverse my substitution, I have x squared plus 17 is equal to 0, and x squared plus 3 is equal to 0. Now, bringing the 17 over and taking the square root, we have x is equal to plus and minus the square root of 17i, the I from the negative 17 we brought over. And similarly, this would be x plus and minus the square root of 3i. Now, it's worth taking a look to make sure that these actually satisfy the original equation. And we'll see why this I is so important. If I plug that back into this equation, well, square root of 3i to the fourth power is really going to be the square of the square. And if I square this, first I get 3, but the I squared gives me a minus 1. So this becomes a minus, and squared again gives me 9. This tells me that my equation should be 9 plus 20 times minus 3 plus 51. And we can see here that 9 plus 51 is 60, but 20 times minus 3 is minus 60, and we get our 0. So indeed, we have the same interpretation of our answers, that when plugging them into this particular equation and following my rules about squaring imaginary numbers, I wind up with a 0. Similarly, here, I would like to take a look at my three terms. I have nothing here. I have a middle term. And here I have the square of the middle term. Well, yes, because r is precisely the square root of r squared. And as such, what I should do here is I should make u equal to the square root of r, because then I have u squared plus 2 times u minus 24 is equal to 0. This gives me that u plus 6 times u minus 4 are my factors, and setting each equal to 0, I get u is equal to minus 6, or u is equal to positive 4. But now reversing my substitution, I wind up with the square root of r equal to minus 6 and the square root of r equal to 4. Squaring both sides, I wind up with r equal to 36, and squaring both sides here gives me 16. But we have to check to make sure that our equation actually works before we check this out for one answer. And I'll just say that when we make a substitution based on a square, we'll be all right. However, when I make substitutions based on the radical, based on the square root, I may actually have introduced solutions here which might not exist. Let's give both a try and see what happens. If I take 36 and plug it in, what I wind up with is problematic, because this is in fact going to be 2 times 6, which is 12, minus 24. And so we wind up with 24 in total and not 0 at all. So actually, 36 was not an answer. It was a fictitious answer introduced by squaring. We can lay that out most plainly with another quick example. Say I knew a solution to an equation was 2. Now, if I squared both sides, I'd wind up with 4. But then applying the square root property, I would wind up with plus and minus 2. Where did this second solution come from? Certainly, if I plugged minus 2 back into the original equation, it wouldn't make sense to say minus 2 is equal to 2. So actually, that doesn't work. It contradicts the original starting point of the problem, and this was a fictitious solution. We can introduce these kinds of solutions when we start to deal with functions which are not one-to-one and trying to find inverses across their entire domain. The square function is such a function, and its inverse as a square root is not a true inverse. We have to be very careful about this, because equations like a squared square rooted equals a is only true when a is greater than 0, or equal to 0, I suppose. Now, what about our other solution? What about our 16? Well, that's going to give us 16 plus 2 radical 16 minus 24, and 2 radical 16 is 2 times 4, which is 8. So we have 16 plus 8 minus 24. 16 plus 8 is 24, so we wind up with 0 here, as desired. So 16 is a solution, but 36 was not, even though it was revealed as part of our usual process. Here's a fun one. Notice here that we have something almost like a difference of squares, except there's a negative here. What then if I chose u to be equal to w to the minus 1? Then u squared would be equal to w to the minus 1 squared. which is in fact, of course, w to the minus 2. So that would read u squared minus 4 equals 0, which we could factor or use the square root property to reveal that u was equal to 2 or minus 2. Let's then rewrite this as two equations. We would then have that w to the minus 1, which is of course 1 over w, was equal to 2, or 1 over w was equal to minus 2. Either taking the reciprocal of both sides or multiplying w up and dividing 2 down, we would wind up with w equal to plus n minus 1/2. And these would be our two answers to this equation. This one's also pretty fun. Take a look. We have something in the middle, we have nothing on the end, and we have the square of that something. So again, we found this pattern of nothing, something, and something squared. We're going to want to take advantage of that by substituting in for our middle variable. Let's say u is equal to x to the 1/3. This makes u squared equal to x to the 1/3 squared, or 2 times 1/3. That gives us x to the 2/3 power. Hence, we have 3u squared minus u minus 2 as our substituted equation. Now, we could use the quadratic equation, but I encourage everyone to factor if possible. So let's see if this equation factors in terms of u. Minus times a plus would give me this minus, and we put a 3 in both places and a 1/3 out front for balance. This is now equal to the line that came before. Now, what factors are we looking for? We're looking at 3 times 2, which is 6, and we would like factors of 6 that have a difference of 1. That's, of course, going to be 3 and 2, and we plug them into these two places. Taking the larger number and putting it in the first slot will always work if you drop this sign straight down. Taking a 3 out and canceling it with the 1/3, we have u minus 1 and 3u plus 2. Now let's repeat our substitution. We would then have, from the first equation, x to the 1/3 minus 1 is equal to 0, bringing our minus 1 over, and taking the cube of both sides would give me x is equal to 1. On the other hand, if I had 3u plus 2 equal to 0, minusing the 2 and dividing by 3, reversing my substitution, we could then cube both sides to get negative 8/27. In the next example, our middle term is a 1/5 and power, and so we're going to want to choose that to be our u. This makes it u squared plus 10u plus 25 is equal to 0, but a quick glance at noting this is a square and this is twice it would give us that this is u plus 5 squared. Now, setting this equal to 0 and solving, we wind up with u is equal to minus 5, and reversing our substitution, taking the 5th power, and reminding ourselves what the 5th power of 5 is, we get that x is equal to negative 3125. We could confirm that this is in fact a solution by plugging in. I will say that we really only have to worry about even roots, that is to say, roots with an even index. For example, a substitution that we would have be equal to a square root or a fourth root will cause that problem functions which are not 1-to-1 as their inverse, like for example x to the 4th or x squared. They're not 1-to-1, and so their inverses are in general not functions. They are in fact multi-valued maps. This is not the truth. This is not the case with fifth powers or cubes. If we have odd powers, these functions are sometimes 1-to-1, and their inverses, therefore, are functions and not multi-valued maps. This means that the substitution won't cause us these problems. But if you're ever in doubt, it's perfectly fine to plug in your answers and make sure that they actually work anyway. But the real concern will be with even roots, like square roots and fourth roots when you make these substitutions. So here we have a nice one. This actually could work if we just expand everything and regroup our like terms. But since we already have this factored form, it makes just as much sense to say, hey, let's just let u be equal to t plus 5. If I do that, this says u squared minus 5u plus 4 is equal to 0, which factors as u minus 4 times u plus 1. This gives me u being equal to 4 or u being equal to minus 1 as roots. And reversing our substitution, we have t plus 5 equals 4 and t plus 5 equals minus 1. Minusing 5, we wind up with t is equal to minus 1, or t is equal to minus 6, respectively. Okay, last one. So let's take a look at this. We have something in the middle, and then something squared as the leading term, and then this term is just a constant. This gives us an indication of what we should perhaps let our u be. Let's let it be 1 over p. In this case, I have u squared, because u squared would be 1 over p squared out front, and plus 2 times u minus 15 is equal to 0. Factoring this polynomial, we wind up with u plus 5 and u minus 3, which have a difference of 2 and a product of negative 15, respectively. Then I could solve 1 over p being equal to minus 5, or 1 over p being equal to 3. Reversing, we find that p is equal to 1/5 negative, and p is equal to 1/3 positive. And these would be our two roots. This, of course, came from u being equal to minus 5 as a root, and u being equal to positive 3 as a root. Okay, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.